It's just one test. It's not like when I started grad school, my teacher was like, this is the most important test you'll ever take. And we're like, that's not a helpful thing to say. And it wasn't. He was a liar. Let's see here. I should be doing things. So if you've already taken the test today, you don't need to be here. You're certainly welcome to be here if you've already taken the test just now, but you definitely don't have to be here because we're just going to take people's questions about the test. So yeah, let me. Let's see. Those of you on Zoom still do, even though I am going to mark everyone present for today, even if they didn't come, still do fill out the attendance form if you came. So let me, for those of you on Zoom, let me give you the attendance form.
I really wish you would set it out so that it wouldn't be like this terms, it will be like lower stakes one, but then we have like.
Yeah, some classes do that. Definitely Professor Burke, not that your 16C teacher is already set. I don't remember who it was. It's not Professor Burke. So there are some teachers that actually do teach math classes that way. I know it doesn't really help now, but like, yeah. So we'll get going in just a second here.
Especially the classic where it's your grades only the midterm and the final.
Right, especially because like I feel like it doesn't like encourage you to do the homework, which is how you learn the material. I mean, I understand why someone would do that. You got to get through the material, and you only have so many days. So I don't blame your teacher. I would give them, I personally would give them a pass on that because I know what that's all about. I know it's not ideal, but we are such a short. Okay, we're good to go here. Right. Positive. I think everyone else is gonna fit. That's what I used to do. Like you all, everyone else is gonna fail. I'm gonna do great. Let's see. Oh yeah, I was gonna do one more thing. Want to find just 1 second. So just so you're all aware, if you're taking 16C next quarter, the co-class for 16C next quarter, it'll have to be a workshop, but whatever. The workshop next quarter will be offered Monday, Wednesday, Friday from 10 to 11. So if you're trying to take 16C and you want to take the co-class workshop, whatever it's called, try to leave that time slot free. Obviously, if you can't, you can still, just like this quarter, we'll be recording it and we'll be posting the videos. So you can always watch the videos later if you can't attend the class in person. So yeah, just wanted to make everyone aware. Next quarter, the co-class, the workshop, because you won't actually register for it. It's fine. Will be Monday, Wednesday, Friday, 10 to 11. You'll still like fill out the thing to be added to Canvas, but there won't actually be like a class you register for on Schedule Builder because it's fine. Let's see here. What am I doing? All right. So you should think about what questions you have. Someone already asked one thing. Those of you, the words. Those of you on Zoom, feel free to type a question in the chat or say words when the opportunity presents itself. Cool. Somebody asked about the difference between a couple of things here, so let's get going. Pens. So I think you mean implicit, but yes. So let's look at this first. So I want to find the derivative of something like 4 to the x cubed minus sine of x. And although you could do this one, the quote unquote long way, where you let y equal it, take the natural log of both sides, et cetera, et cetera, et cetera. But you only really have to do that if your base and your exponent have variables. If your base is a constant, then you can just say, well, I'm going to use the rule that says if my function is 4 to some stuff, or some base that's a constant to some stuff, The derivative is the same thing, 4 to the stuff. And then we have to multiply by two things. We have to multiply by the derivative of the stuff, good old 3x squared minus cosine of x, and also the natural log of 4. Just like if you were to take the derivative of e to the x cubed minus sine of x, the derivative is e to the stuff times the derivative of the stuff. And although we don't usually write it, you could write times the natural log of the base. It's just that in this case, that's equal to 1. So we don't just write it. So if your base is a constant, you can do it this way. You can also do it the long way. On the other hand, if your base is not a constant, so if you say I have a function, and usually if the person is not a total jerk, they'll say find dy dx for something like y equal to yeah, I'll do that, sure. Let's say it's x to the 3x, so sure, I'm gonna make it weird, the 10x. So first things first, if you see something like this, where it's x to a power, instead of just like power to a power, simplify it first. Rewrite this as x to the 3x times 10x is 30x squared. That's what we should do first. Now, there's two different ways to do this. I've been showing you all one way to do it, which I think is the superior method of doing it. And I'll show you that first, but then I'll also I'll show you the other way just because I know that's how your teacher is doing it. And it's a perfectly valid way of doing it. But the way I think you should do this is you're going to take the natural log of both sides. So the natural log of y equals the natural log of x to the 30x squared. I should be very, very explicit here. We can't do anything about that x squared, meaning you can't bring that 2 down and multiply it. It's just kind of stuck there, which is fine. It's going to be okay. But once you've done this multiplication of a power by a power, you can't kind of bring anything else down like we would maybe like to. But the whole reason for taking the natural log is so that we can bring this exponent down in front. So then we're going to get the natural log of y equal to 30x squared times the natural log of x. I will point out to the comment on Zoom, this is a small example of an implicit differentiation problem. I mean, it's not really, but it does have some of that flavor in it. So then we differentiate both sides. And we use implicit differentiation on the left to say, oh, the derivative of the natural log of some stuff is going to be, like, you should all be able to write it down. I'm going to write it down in secret. You also write down what the derivative of the natural log of y is. Okay, I got my answer. Okay, write it down. Okay, I got 1 over y prime. I hope you did too. And on the right-hand side, you're almost always going to have to use the product rule. So I'm going to think of this piece times this piece. So the derivative of 30x squared is 60x times the other piece not differentiated plus flip it up. Leave the 30x squared alone, multiply by the derivative of the natural log of x, which is 1 over x. 2 steps left. I like to do them in one go. We're going to multiply both sides by y, and we're also going to replace y with what it's equal to. It is pretty standard to replace y with what it's equal to in its original form. Meaning, even though I could rewrite it as x to the 30x squared, it's more typical to write it as how you've originally expressed it before you did any simplification. So I would probably default to writing this as y prime equal to y, which is, gosh, capital all over the place here, x to the 3x to the 10x, or if you prefer, x to the 30x squared, times all of this, which I am going to simplify just slightly. 60x times natural log of x plus 30x squared times 1 over x simplifies to just 30x. And yes, you could pull out a 30x as a factor if you wanted to, but there's no good reason to. So I would leave it like this. Or you can do this other thing, which really is going to be pretty much the same amount of work. The other thing we do, or that you can do, is rewrite your y as e to the natural log of x of your stuff. What I mean is, I'm going to take my y equal to x to the 3x to the 10x equal to x to the 30x squared. And I do still think you want to do the simplification before you do anything else. If you have a power to a power like that. And then we're going to rewrite this as y equal to e to the natural log of whatever you've got. X to the 30x squared. That's the other way of doing this. I don't love doing it this way, but it's totally valid and fine. Okay, sorry, got all these pens in here. Just like before, that power is going to come down. So we're going to get y equal to e to the 30x squared comes down. I should do the little circle thing. Right, this comes down in front of the natural log. So it's still in the power. So I'm going to have e to the 30x squared times the natural log of x. And now the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So we're going to get e to the stuff, which is e to the 30x squared times natural log of x, times the derivative of that stuff, which is the same product what we did in the other version of this problem. It's going to be 60x times natural log of x plus 30x squared times 1 over x. Now, a couple things to note here. As is typical, people usually at the end of this go back and say, oh, well, I could write e to the 30x squared times natural log of x, but I could say that's really the same as that, which is the same as that, which is the same as that. So it's very common practice to also replace this with its original form. So we often like to write this as dy dx equal to original form, right? This is just the original thing you started with, which is x to the 3x to the 10x. Again, probably not required, but is just a fairly common practice. And then this is all the same as it was. 60x times natural log of x plus 30x. Doing it this way doesn't require using implicit differentiation like we did in the previous way, right, where we had the derivative of the natural log of y is 1 over y prime. But other than that, they're pretty much the same.
You don't think it needed like
You probably can. I mean, there's technically there's no reason you shouldn't be able to live like this, other than your professor might prefer you to not. I don't, but other than that, like I can't really say. Okay, sorry. Let me grab these practices. I'm just easy to practice. Too much stuff. Had it in here. Sorry, there was. So somebody asked about doing an implicit differentiation problem. We totally can. And I think from what I've seen on most of your practice exam problems is typically you're using it to find the equation of a tangent line. Not that that's always what you do, but if that's the variety of question you've got, then there is a way to make it less terrible. Here's what I mean. Let's say, I'm just gonna make some shit up. Let's say we're given the following. We have that, this is where I always get dicey here. Let me make something up that's not too terrible. Let's say we've got 3y squared x plus x to the 4th y. Sure. Equal to e to the x minus 1. And let me make sure this comes out right. 12, 14, 1, 13, sure. Plus 6y plus 1. Let's say that's our equation. And we want to find the equation of the line tangent to this graph at the point, what did I decide on here? I think it said on the point 1, 2. Let's make sure. And so, and I should say, yeah, I shouldn't say anything actually. What I was thinking about was the fact that does 1, 2 actually make this equation work? But you should never think about that if you're given this kind of question. You should just go with the flow and be like, okay, there's the equation. They clearly want me to differentiate to find the slope. I don't care, although it should actually plug in and work. It doesn't matter if it does or it doesn't. That's not what they're asking you to check. So go at this point, and then to find the equation of the line tangent, all you need is a point. We already have one. It's 1, 2, and we need a slope. And that's, of course, where we find the derivative evaluated at the given point. So our job, and then the equation, of course, is going to be y minus the y coordinate equal to the slope, which we're going to find, times x minus the x coordinate. So really, most of the information we need is given to us except for the slope. So we got to find the slope. And to find the slope in calculus, we take the derivative, right? That's how we find the slope typically in calculus. You take the derivative and then you plug in the point that you actually want to find the slope of the tangent line at. So we're going to take the derivative of both sides, just like you usually do with implicit, remembering that y is a function of x. So whenever you differentiate y, you're going to get the derivative of y, not just one. So the derivative, so here I'm going to use the product rule. I've got 3y squared times x. The derivative of 3 times stuff squared is 6 times your stuff times the derivative of your stuff times x. Plus, then we switch it up. We leave the 3y squared alone, and the derivative of x is 1. We have to use the product rule again. We have x to the 4th times y. The derivative of x to the 4th is 4x cubed. Leave y alone. Plus, now x to the 4th gets left alone. And the derivative of y is the derivative of y. Y prime, dy dx, the derivative of y. Equal to, I'm running out of room here. Let's see. The derivative of e to the x minus 1 is e to the x minus 1 times 1, if you want to think about the chain rule there, right? The derivative of e to the stuff is e to the stuff times the derivative of the stuff. And then derivative of 6y is 6 times the derivative of y. And the derivative of 1 is 0. Do be careful. I've seen too many people leave that as a 1 because they just like, oh, the constant's it. No, derivative of a constant by itself is 0. To make sure those go away. Now, here is what I would say is the crux of making this easier than it, or not as hard as it needs to be. At this moment is when you plug in your point. Don't wait until you solve for y prime and then plug it in after. I don't want to deal with all this trash here. I'm going to plug in x equal to 1 and y equal to 2 now. It's totally allowed. Now, I should say, this is only valid if you're trying to find just the tangent line or the slope of the tangent line at one particular point. If you're trying to find the derivative in general, you have to solve for y prime in terms of x and y. Yeah, Maya.
Why is the derivative of y?
Sure. So let me ask you a different question. What's the derivative of 6 times x to the 7th power? What's 6 times 7? Here's what it is. The derivative of this is 6 times 7x to the 6th. Does that seem okay? So right, because when you have a constant times a function, the derivative is the constant times the derivative of the function. So down here, right there, I have a constant times a function, right? Because we're making the implicit, that's why it's called implicit differentiation, assumption that y is a function of x. So when I differentiate this constant times this function of x, I get this constant times the derivative of that function of x, just like I did here, right? This constant times that function is that constant times the derivative of that function. The other way you can think about it, if you prefer, you can say, oh, like the derivative of, so for example, the derivative of y squared is 2y, and then you multiply by y prime. The derivative of y is 1, and then you multiply by y prime. You can think of it that way if that's a better way to think of it for you. But whenever you're differentiating something with y in it, you always should be getting a y prime popping up. Sometimes it's just y prime like here. Sometimes it's something with y and then times y prime like over here. The rest of this is arithmetic and algebra. So I'm going to plug in x equals 1 and y equals 2, and I'm going to be very careful about it. I'm going to get 6 times 2 times y prime times, okay, I'm not going to write times 1, plus 3 times 2 squared, plus 4 times 1 times 2, plus 1 to the 4th times y prime, equal to e to the 0, plus 6 times y prime, oh, and great plus 0. And then I identify all my y primes. So I'm going to bring them all to one side and everything else to the other side. So I've got 12 y prime plus y prime minus 6 y prime. I'm going to leave that on the left. On the right hand side, I'm going to have I'm going to have an e to the 0, which is 1, and subtract off 3 times 4 and 4 times 2. So 12 plus 1 is 13, minus 6 is 7. So I have 7y prime equal to 1 minus 20 is negative 19. So my slope is negative 19/7. That's my slope. And then we go back to our equation and we say, okay. These top, they want to stay on. Stay. Fine, it doesn't really matter, it just bothers me. So then our equation is going to be y minus 2 equal to negative 19/7 times x minus 1. Most people are probably going to ask you to write the equation of your tangent line with y by itself. So if you want to be not thinking too hard about it, you could just say, well, okay, fine. You said y by itself. Sure. Y equal to negative 19/7 times x minus 1 plus 2. And that's okay. They might ask you to say what the y-intercept is if they're being real kind of persnickety about it. So we can multiply this out and get negative 19/7 x. And negative 19/7 times negative 1 is plus 19/7. Plus another 14/7 is going to be plus 19 plus 14 is 33/7. That's probably the more standard way of writing your answer. But if I wasn't asked to write it in a particular way, and I've got, not all the time in the world, I would leave it like this, because that shows that you found all the things you need to find. You know how to write the equation of a line. That's the technically correct answer. And then if you got time at the end, come back to it and write it as y equals. Or don't if they didn't ask you to. Right? If they didn't ask you to, like if they just said find the equation of the line, and your professor hasn't been like, you need to write it as y equals, leave it like that. Don't give yourself a chance to make mistakes by doing more math than you need to do. All right. Other questions, either from the practice exams or just things you want to ask about or hear about? Yeah.
Back to the point, like the 6y on the very top line.
Mhm.
If I saw that, I would be like thinking product rule.
You could use product rule there. So let's think about whenever you do the product rule of a constant times a function. Let's do it for this one. So I have derivative of 6 times x to the 7th, and I use the product rule. I'm going to get the derivative of 6 times x to the 7th plus 6 times the derivative of x to the 7th. Let me ask you, what's the derivative of 6? 0. So you're getting 0 times x to the 7th plus, oops, I forgot the prime there. Apologies. Plus 6 times 7x to the 6th. So the idea, if you can totally use the product rule for a constant times a function, but what always ends up happening is if you're taking the derivative of a constant times a function, and you're going to use the product rule, okay, it's the derivative of the first thing times the second thing plus the first thing times the derivative of the second thing. And the derivative of that constant, that's going to be 0. Which means this whole piece is 0, which means we just end up with the constant times the derivative of the function. And that's really where the constant multiple rule comes from, is that when you differentiate a constant times a function, this half of the product rule just goes to 0, and the other half of the product rule is the constant times the derivative of your original function. So yeah, that's what's happening there. So the same deal for, right, so if you're taking the derivative of 6 times y and you're using the product rule, you're getting the derivative of 6 times y plus 6 times the derivative of y, and then this part is going to go away. That's one way of seeing that. Typically, we try not to use the product rule if it's just a constant times a function, because we can just use the constant multiple rule, but it's always fine to use the product rule as long as you're careful about it. Yeah, man. Yeah, go ahead. Which one is it? Sure. Fall 2021. Sorry, which part? 5D. Sure. So we've got the integral from 0 to 3 of e to the 2x times the square root of e to the 2x plus 1. So I should ask all of you, when you see this integral, what method of integration is screaming at you? Yeah, u sub is screaming. And what's our choice for u? Yeah. Stuck inside another function. And more importantly, its derivative is e to the 2x times 2, which we have essentially got right there. We just don't have the times 2, which is totally fine. Okay. Has your professor talked about how they want you to deal with u subs for definite integrals? Like, do they want you to change limits of integration? Do they want you to leave them as is? Great. That's in my opinion the better way to do it. So let's do that. So first of all, I'm just going to start if I'm doing a U sub with a definite integral, let's deal with the change right away. We're going to say, okay, if I'm going to leave myself room here, so we'll go down here for a second. So if x equals 0, then u is going to equal e to the 2 times 0 plus 1. You're literally just plugging in the x value into your u thing and getting what u is. So e to the 0 is 1, and 1 plus 1 is 2. So this x equals 0, that's going to get replaced with u equal to 2. Similarly, although not as nicely, x equal to 3, well, again, we're just going to throw that into our u equation. U is going to equal e to the 2 times 3 plus 1. And that's, unfortunately, we're just stuck with e to the 6 plus 1. Sorry, that plus 1 should not be in the exponent. Apologies. E to the 6 plus 1. So that's what's going to be our upper limit of integration, which is not particularly nice, but you get what you get. Okay, so now we're going to rewrite this in terms of u. So this is going to become, oh, I guess I didn't do the one thing over. I should isolate my dx. Sorry, I forgot about that. So I'm going to get du divided by 2e to the 2x equal to dx. So I believe that's the way your professor likes to do it, even though not my favorite. It's fine. Not everything has to go my way. So I'm going to be going from u equals 2. I do like writing u equals, just so the person who's reading my work knows that I know what I'm doing. And then up here, I'm going to write u equals e to the 6 plus 1. Maybe the first time. Maybe after that, I wouldn't write u equals every time. But the first time when I'm changing from these to these, it's nice to be like, oh yeah, they know what they're talking about. And then we're going to have this e to the 2x, the square root of u, and then our du over 2e to the 2x. And our goal, you have to make sure that this variable that's under the du, that has to cancel. If that doesn't cancel, you can't go further. Because you have to be able to write the entire integral with your new variable u and none of your old variables x. X is out, u is in. So then we rewrite this a little bit. I'm going to take this 1/2 here that's still there, put it out in front of my integral because it just makes it easier. And then I'm integrating from 2 to e to the 6 plus 1 of u to the 1/2 du. Great. We have now written this as a very easy thing to anti-differentiate in terms of the variable u. So now we're going to anti-differentiate it. So we're going to get 1/2 times the antiderivative of u to a power, unless it's the -1 power, right? If it's u to the -1, the antiderivative is the natural log of the absolute value of u. But that's not what we have. We're going to get u to the 1/2 plus 1 divided by 1/2 plus 1. You don't need to show all this work, but if you're not exactly sure, it's not like if you have trouble maybe adding 1/2 plus 1, it's good to show this so the person, again, grading it kind of has an idea that you know what you're doing. All right, 1/2 plus 1 is 3/2. So we're going to get 1/2, and instead of dividing by 3/2, we're going to multiply by 2/3. And then we're going to have u to the 3/2 evaluated from 2 to e to the 6 plus 1. So finally, we're going to I would do, okay, fine. I'm going to simplify this first part as 1/3 because the 2's cancel. But then we're going to plug in. And we're going to get 1/3 times e to the 6 plus 1 to the 3/2 minus 2 to the 3/2. And there's nothing else we can do with this. That is as good as it gets. Neither of those things. It's not like we have like 9 to the 3/2, which you could simplify as 27. You have gross numbers raised to gross powers. You leave it as is. Questions about any of the things we did in this process? This 1/3 here? Because I didn't want to write it twice. But the better answer to your question is because I can. So we could totally have written this as 1/3 times e to the 6 plus 1 to the 3/2 minus 1/3 times 2 to the 3/2. But if you have a constant multiple of the stuff that you're about to plug into, that constant multiple can totally just live on the outside and be, as long as you make sure to put parentheses or brackets around the stuff so that you are showing that it is going to distribute each of those things. So really, because I'm lazy and I can. But honestly, you should too, right? Like, I think it's better to write this than to write this. I don't want to write that 3/2 twice personally, or sorry, the 1/3 twice personally, but it's certainly fine to write it either way. But so I guess, let me, one more thing. Okay. So really I could say this is equal to 1/3 times u to the 3/2 from, that's kind of the work I'm really doing, I guess. Okay. Where did the, sorry, say that one more time? The -2 because so right, whenever we evaluate a definite integral, right, whenever we're finding the area under a curve, you're always finding the antiderivative, whatever that is. So let me just show one more step here. So right, here's my fully simplified antiderivative. It's 1/3 u to the 3/2, but then that's just the function. I want to know how much area I've got. So I have to plug in my limits of integration. And whenever you plug in your limits of integration, it's always the top one first minus the bottom one second. So I'm getting 1/3 times the top limit plugged in for u to the 3/2 power, minus, then I'm getting 1/3 times the bottom limit plugged in for u to the 3/2 power. So it's always, whenever you're doing a definite integral, you find the antiderivative, and then after that you plug in the top thing, and then minus you plug in the bottom thing. Always top plug in, minus bottom plug in, never the other way around. So you can do it a different way, but this is the way that you all just told me that you said your teacher wants you to do it. But here's the other way of going if you prefer. The other way is to not have found these other limits of integration. So I don't want to deal with that. So the other way you can go is to say, once you get to here, you can instead plug back in and say, okay, well, instead of 1/3 u to the 3/2, I'm going to say that that's equal to 1/3, and I'm going to plug back in my x, or sorry, what u is equal to, which is, let me see, our u was e to the 2x plus 1, right? Yeah. So I'm plugging back in e to the 2x plus 1. But now my limits of integration shouldn't be u values anymore, right? This was a u equal to 2 and a u equal to e to the 6 plus 1. Now I'm back in the land of using x. So I have to have x variables, which were x equal to 0 to x equal to 3. It definitely should give you the same answer. And it does, right? If we plug in 3 first, we get 1/3 times e to the 2 times 3 plus 1 to the 3/2 power, minus, if we plug in 0, we get 1/3 e to the 0 plus 1 to the 3/2 power. Those are exactly the same. Yeah, Maya.
And in this situation, we're not changing the limits.
Correct. Right. So if you had done it, if you had decided to do it this way, you would not have had to have done the work of finding these new u limits of integration, because your plan of attack was to use a u substitution, anti-differentiate, then plug back in what u is equal to, and then plug in your x values. Either way is fine, but you have to make a choice. You have to decide which way you're going to do it. So if you're doing a definite integral that's going to require a u substitution, you can either change limits of integration like we did here, or not. The only thing I will warn you against is if you decide not to change limits of integration. So let's say we were doing this work, we did our u sub, and we went from this first step of the integral from 0 to 3 of e to the 2x times the square root of e to the 2x plus 1 dx. And I started rewriting it in terms of u. So I've got the integral of e to the 2x square root of u du over, sorry, brain, 2 e to the 2x. It's wrong once you cancel those x's, it's really incorrect to write the limits of integration as 0 and 3, because they're not. So people typically, if they're not changing limits of integration, what they often do is they either just don't write them, or they write them as what the x values would have been, but they actually don't just write 0 and 3. They write, oh, this is still x equals 0 and x equals 3, so that they know that you know what you're talking about, that you know that those aren't your new u values. So I personally would encourage everyone to do it the first way, where you do change limits of integration, but you don't have to do it that way. You can do whatever you want. That's just the way I like to do it. It's like, it kind of avoids the whole having to be like, well, I've got this integral and it's got u's in it, but I didn't find the u value. So it avoids that mess, for lack of a better word. Can I talk about how to differentiate e to the x, y? Okay, sure. So yeah, so that's definitely also an implicit problem. So if we look back at, I'll just grab this one over here. Sorry, where'd you go? Oh, fine. Sorry, I've got it here. I guess I'm not going to do the whole thing, but I think you've got it. I thought I had the spring one here. There it is. Okay. So it's the same reason as the implicit stuff before. But let's talk about it. So if I have the implicit equation, e to the xy plus the natural log of y minus e. I'm going to change it up just to make it more fun. E to the x plus y to the fourth equal to e minus e squared plus pi cubed, just for fun. Similar to problem 3, but not quite the same. So if we're trying to do the thing where we find y prime, so we can find the equation of the tangent line at a point, if I'm going to differentiate both sides, all right, well, the derivative of e to the stuff is e to the stuff times the derivative of that stuff, which I'm going to do in another step. And then the derivative of the natural log of y, or the natural log of some stuff, because y is some stuff. It's not just a variable. It's 1 over your stuff times the derivative of your stuff. And the derivative of e to the stuff is e to the stuff times the derivative of that stuff, which again, I'll do in the next step. Equal to the derivative of e is, the derivative of e squared is, the derivative of pi cubed is, they're all 0. There's no x's over there. There's no y's over there. There's no variables over there. Those are all constants. E is about 2.7, e squared is like 7.8, and pi cubed is like 30. Those are all, that's just one big constant on the right hand side. It's a terrible number, but there's no variables. If you see no variables, derivative is 0. So then, continuing on with this, we would get e to the xy times, okay, so now I have to use the product rule for the derivative of x times y. What's the derivative of x? What did I multiply by? Just y, right? Derivative of one part, not derivative of the other part. And then we add and we flip it. We leave the first part alone and we multiply by the derivative of the second part. So that's why you're getting e to the xy times y plus xy prime, because you're having to use the product rule to take the derivative of the xy part, which is the chain rule part of that derivative. So that's why that's happening. To finish this off, well, to finish off the derivative here, I would write this as y prime over y minus e to the stuff. And then the derivative of x plus y to the fourth is 1 plus the derivative of y to the fourth is 4 times my stuff to the third times the derivative of my stuff. And then you would plug in whatever point they gave you now to try and solve for y prime. But I don't think we need to do that because we already know that. Cool. Excuse me. Other questions? Yeah.
Can you do a trig you said?
Sure. Yeah. Okay. How gross do I want to make it? Not that gross. Okay. So let's say we want to do the integral of the square root of secant of 6x. Well, I could have made this more terrible if I wanted to, but I won't. I feel like with the trig ones, they usually try and make the u subs not too awful. So I got the integral of the square root of secant of 6x. I was making the cube root of secant of 6x. It's not for fun. Times secant of 6x tangent of 6x. So the idea, whenever you see something that looks terrible, you've only really got one tool so far. right? I mean, maybe two. You've got two tools. One tool for integration is simplify the heck out of the thing, right? If you've got something like the integral of, x to the fifth plus 3x squared minus x to the negative second over x to the fourth, you're just dividing each term by x to the fourth, and then you've got powers of x, right? That's just the integral of x to the 1 plus 3x to the negative 2 minus x to the minus 6. And then anti-power rule till the cows come. But you can't simplify the thing, so you just get x to a power, x to a power, x to a power. Your other tool that you have is a u sub. And that's kind of it right now. I'll say there's maybe one exception to that, which I'll talk about in a minute. So I don't see a way to simplify this. Technically, if you really wanted to, you could say secant of 6x to the 1/3 power times secant of 6x to the 1 power. You could add those power and get secant of 6x to the 4th power. No one, they're trying to write it in a way so you can see what you need to do. The plausible choice for you here is secant of 6x, because it's stuck inside the cube root, and more importantly, its derivative is secant of 6x tangent of 6x times 6. Sure, the secant of some stuff is secant of the stuff times tangent of the stuff times derivative of the stuff, which is 6. And then it's a very quick little trip to get to du over all that stuff. Du over secant of 6x tangent of 6x equals, sorry, brain, 6 dx. So then I'm going to replace, sorry, I always want to do it the other way. Sorry. Divide both sides by the 6 too. I'm sorry. I just never want to do that. Okay. So then rewrite the thing. And remember, when you're rewriting the thing, you cannot have any x's left over. You have to keep rewriting it until you get just u's. So I'm going to have the integral of the cube root of u, and then I'm going to have, sure, do it this dumb way, secant of 6x tangent of 6x times dx over 6 secant of 6x tangent of 6x. And of course, the things with x's in them, sorry, I know it's hard to see because they're kind of small. Sorry, it's not helping you all though. I know, I just made it terrible. I do, thank you, good call. So, but let's pretend I didn't. Let's pretend I made a mistake and I didn't see that. So if once I do this, I cancel this and this and that and that, and then I rewrite it as the 1/6, the integral of u to the 1/3 d. Oh, dx would be a problem. So that's when I would go back and be like, oh, I didn't mean to write dx. I really didn't mean to write du. Because your end result before you integrate should only have u's, including the d whatever. In fact, the d whatever is the most important part. That part needs to change from dx to du. And then the rest is not too terrible. We get 1/6 times u to the 1/3 plus 1 is 1/3 plus 3/3, which is 4/3. And instead of multiplying by, or sorry, instead of dividing by 4/3, we multiply by the reciprocal, just 3/4. Since it's indefinite, or it's not an area, we have to tack on a plus c. And of course, I don't have enough room, so I'll move it over here. Sorry, got super close here. Let me zoom back out a little bit so you can all see what I'm doing. Sorry, got to do 2 zooms at once here. It's impossible. Okay, so just simplifying this, 1/3, or actually 1 times 3 over 24 is going to be 1/8. And then I'm going to have, instead of u to the 4/3, I'm going to have secant of 6x to the 4/3 power. Plus c. Remember the plus c. It's worth a little bit. Plus c when it's indefinite, right? When there aren't limits of integration, but when it is a definite integral where you're finding like the area, you don't need the plus c at all. Okay. There was one thing I alluded to about methods you have to integrate things. So 2 things I'll say, I didn't unfortunately have the time really to look through all these practice tips. I don't really know if I saw any of them on there, but I will say that one thing you could be asked to do is to find something like the integral from -9 to 0 of 5 times the square root of 81 minus x squared dx. And this is not a situation where you can simplify. And this is not a situation where you can do a substitution. This is a situation where you have to know that the function y equal to the square root of 81 minus x squared is the top half of a circle of radius 9 centimeters to the origin. So this function looks like this. And so I would take this integral, pull out the 5 because the 5 is just showing off over there. And then I would say, oh, look, this integral from -9 to 0 of the square root of 81 minus x squared, that is just the area under this curve. But that's just 1/4 of a circle of radius 9. So this is equal to 5 times 1/4 of the area of a circle of radius 9, or 1/4 of pi times 9 squared. And I probably wouldn't do anything else. Probably just leave it like that because I don't want to multiply 5 times 81. But you could. You get 5 times 81 pi all over 4, which is 405 pi over 4. That's not really the point. The point is that if you see something like this, square root of number squared minus x squared, and one or both of your limits of integration are that number that's being squared or it's negative, it's a pretty good bet it's going to be part of the circle. Either a quarter or half, depending. Like if it was from -9 to 9, it would be the entire top half of the circle. If it's 0 to 9 or -9 to 0, it's just it's half of the top half. Quarter. The other thing you could see, and again, I don't know if I saw this really, but you might see, let me double check here before I get too crazy here. I don't know, half-life, yeah. No, I don't think so. You could see the integral of an odd function, but I'm not really seeing that on any practice test. So, but someone could ask you something like, what's the integral from -3 to 3 of, let's make it stupid, like, sure, x to the 4th plus x squared plus 1 all over, I blew it. I'm gonna flip this over because it doesn't really matter, but it matters to me. Let's say we had x cubed plus x over x to the 4th plus x squared plus 1. It might be possible to integrate that. It might be. You probably could try. Like, this would be a good trick problem. Because you're like, well, I can maybe do a u sub there. Because it kind of looks like if you let u equal x to the 4th plus x squared plus 1, your du is 4x cubed plus 2. Oh, I'm so close. If only that was a 2x cubed plus 2x, I could factor out the 2 and I'd have x cubed plus x. But it's not, and it won't ever work. Here's what this question is actually getting at. Notice that those are opposite signs of each other. Notice that this function inside here is an odd polynomial divided by an even polynomial. That is an odd function. And if you go from negative number to positive number of an odd function, you get 0. I don't know if that will come up, but it's good to be aware of. What else? Yep, go ahead. Like for exponential growth or decay?
Yeah, because they had a couple of true.
Sure. Let me look at those actually real quick. So here's what I'd say. You can tell a function you can tell like y equals c to the kt or that kind of deal. You can tell it's growth if k is positive. You can tell it's decay if k is negative. So for example, looking at say 1g from, well, let me just write it down instead of trying to have you all look at the thing. So for example, this function f of t equal to 5e to the negative 3t is for sure decaying because that coefficient is negative. If you're not sure though, one thing, you can do is either plug in some values. I know it's not super easy to plug in values, but for example, like if I plugged in 0, f of 0 is 5e to the negative 3 times 0, which is 5 times e to the 0, which is 5. And if you plug in a bigger value, so if you plug in a bigger value, if the result gets bigger, it was growing. The result gets smaller, it was decaying. So if I plug in a larger value, like, I don't know, 2, f of 2 is 5e to the negative 3 times 2, which is 5e to the negative 6, which is easier to see that it's getting smaller if I write it as 5 divided by e to the 6. Oh, that is much smaller than 5. So this is totally decaying. The other way to do it, if you really wanted to, is if something's decaying, that means the function is decreasing. And a function is decreasing if its derivative is negative. So you could say, oh, instead, I'm going to take the derivative. I think this is all too much work. Like the point of this question is just to be like, I can see it's doing it. But if you're not sure right off the bat, you can take the derivative and say, oh, the derivative is 5e to the stuff times the derivative of the stuff, which is going to give me negative 15 e to the negative 3t. And even though this is decaying, it's always positive. Or sorry, it's always negative. Negative 15 is negative. E to the anything is positive. So this is always going to be negative. And if the derivative is negative, the original function was decreasing or decaying. Let me see one thing, because I feel like there was another one that looked like it was a little more hidden if it was positive or negative. Yeah. You remember what it was? I'm having trouble finding it. Yeah, I knew I saw that one. So if it was, so here's the one that's the trick. So I'll answer your question in a second, Gabriel. Is natural log of 0.5 over 7 a positive number or a negative number? So here's the thing to think about. If you have a stupid natural log power there, think about the graph of natural log. Oh, I've never told you guys the trick. Look at your right hand. Look at your right hand. Everyone, look at your right hand. Mine's not the best, but it's all right. So on your right hand, if you're right-handed, put down your pencil. Your right hand. There's e to the x. There's the natural log of x. Some people have better hands than I do for this, but mine's, I've got old hands with lots of lines on them. But there's those two graphs. So if you're ever not sure, if you're right-handed, which most of you are, statistics, put down your pencil, look at your right hand, yes, right hand. The other hand is, that's going to be e to the negative x and the natural log of negative x. If you look at your right hand, you're going to get e to the x natural log of x. So the natural log of x, looks like this. And let me ask you all, where does it go from being negative to being positive? What's that intercept? 1. So if you plug in a value like 5, the natural log of 5 is a positive number. If you plug in something less than 1, like 1/2, the natural log of 1/2 is a negative number. So the natural log of 1/2 is negative. So this is a negative number, which means this whole thing is decaying or decreasing, whatever way you want to say it. That's how you deal with that. That's it. Someone asked here, how do you know that it was 1/4 of a circle instead of 1/2 of a circle? So the way I knew it was 1/4 of a circle was based on the limits of integration, because the limits of integration were as far left as -9 and as far right as 0. So I had to stop right there at 0. That's how I knew it was 1/4 of a circle instead of 1/2 circle. Best of luck on your exam. I think you all do perfectly fine. Try not to stress too much about it. Stop studying before it, like a half hour at least before the test, to give your brain time to like recharge a little bit. Don't just study for the next 3 hours or 4 hours. Give yourself a break. 2 hours. Oh, it's a 5. Okay. So maybe study a little bit if you want to, but give yourself a half-hour break. Maybe eat a little something before the test. You're all welcome. Oops. What's up?
I was just wondering, what is the integral of this?
It is the natural log of sine. Is something you guys have learned. So the way to deal with that specific integral, if it gets asked, it's a u substitution. The integral of cotangent is the integral of cosine over sine. And so you let u equal sine of x, and then your du dx is cosine of x. So u over cosine of x is equal to dx. So then we rewrite this as cosine of x over u times dx, which is du over cosine of x. Those cancel with the integral of 1 over u du, which is the natural log of the absolute value of u, which is the natural log of the absolute value of sine. That's how you do that. Same kind of thing works for for tangent as well. So if you're integrating tangent, it's sine over cosine. You let u equal cosine, same process.
Thank you.
You're welcome. So,
Just wanted to keep it explain this a little. I went to her office hours and she was describing this. And I
totally.
don't remember.
So really, if you don't want to remember that, you can just do a u sub.
Okay.
So let me write it down. So if I'm integrating e to the, was it kx?
Kx dx.
Right. So really it's because of a u sub. So I'm going to let u equal k times x. My derivative of a constant times x is what?
The constant is 0.
Well, if you're going to use the product rule, sure. But I'm thinking of a constant times my function x to the first. So the derivative is going to be my constant times what's the derivative of x? Right.
Okay.
Just
So-
like
so we're not using the product rule because it's e, or
no, we're not using the product rule because we don't have. You totally could use the product rule. You could say, or it's going to be the derivative of k, which is certainly 0,
Okay.
times x plus k times the derivative of x. But that's 0 times x plus k times 1.
Oh, so you just skip that step.
Right, exactly.
Okay.
But I want to really emphasize here, whenever you have a constant times a function, the constant gets to hang out and you can multiply just by the derivative of the function.
Okay.
So now check this out. You have du over k equals dx. We're going to replace. So we're going to get the integral of e to the u times du over k. Oh, that's what the division by k is coming from.
Okay.
So then we get 1 over k integral of e to the u du, but the integral of e to the u is just e to the u. And then we replace u with what it's equal to, which is k times x. And we get 1 over k times e to the k times x.
Okay.
Now, the thing is, the reason your teacher is talking about this as a rule is they would like for you to not have to do this u substitution every time you integrate like e to the 3x or e to the 5x or e to the 1/2x. So whenever you integrate something like e to the 3x, we can kind of just say, oh, the integral of e to the 3x is going to be 1/3 times e to the 3x.
Okay.
And it really kind of goes back to the thing I've said a lot of times, that if the derivative of something would make you multiply by a constant, an antiderivative is going to make you divide by a constant. So if you were differentiating e to the 3x, you would get e to the 3x times 3,
Okay.
because it's times the derivative of the stuff. So when you anti-differentiate e to the 3x, you get e to the 3x divided by 3.
And let's say I'm just uncertain on the exam, I just go through the whole thing.
You use that for sure. You're welcome. You're gonna do great, Maya. You're welcome. I'll see you on Friday. Oh, I should stop the Zoom. Bye, Gabriella. You're not there anymore.